Hello and welcome to Chapter 2, Section 2.5, which deals with something that I really personally enjoy, zeros of polynomial functions. So what are we doing today? We're going to use the fundamental theorem of algebra and also introduce the fundamental theorem of algebra to tell how many number of zeros a polynomial has. Then we're going to find rational zeros. Then we're going to find conjugate pairs of complex zeros. And then we're going to talk about finding zeros by factoring. And then another one is we're going to be introduced to Descartes' rule of sign and the upper and lower bound rules to find zeros of polynomials. And that's pretty much sums it up. So let's start with the fundamental theorem of algebra. Okay, so up to this point, we've been thinking about zeros of functions of polynomials as real zeros, where they cross the x-axis, right? But what if we want to also talk about complex number zeros, where you have a complex number that when you put it in the function, it gives you 0 back. Now, you might not be able to see that on a graph, right? But we do need to consider them. So the fundamental theorem of algebra has been proven by Gauss, and basically this is what it says. It says if you have a polynomial of a certain degree where the degree is positive, then you have at least 1 zero in the complex number system. And in fact, every polynomial function to the nth degree has exactly n zeros as long as you don't as long as you count for multiplicity. Like if a zero happens twice, then you count that, then there's going to be exactly n zeros, and that's including complex numbers or not complex numbers. So here we go. So using that idea and the understanding that zeros are equivalent to factors in the form x minus a or k or whatever you want to consider the zero, whatever letter you want to represent that zero, we have this theorem that if you have a polynomial of nth degree that's positive, then that polynomial f has exactly n linear factors where you have some factor in the front, some a sub n, you factor it out, and then you can rewrite that polynomial in terms of like linear factors where x is a number times x is another number times x is another number, where you can have complex numbers. So these theorems don't really tell us how to find the zeros. It just tells us, they tell us that they exist, okay? And this kind of theorem is called existence theorems. Okay, so let's do some examples. So let's think about this first degree polynomial. F of x is equal to x minus 2. It has exactly 1 0, right? It's a line that crosses through the x-axis at 2, right? So, I mean, yeah. So the 0 for, f of x equals x minus 2 is just 2, and that's 1. And since it's first degree, that's it. We can't find it anymore. So also when I say complex numbers, remember that the complex numbers include all real numbers and imaginary ones. So all the constant terms are included. This technically is a complex number, but it's 2 plus 0i, yeah? Okay. So anyways, let's consider the next example. You have x squared minus 6x plus 9. If we factor, we get x minus 3, x minus 3. In other words, it's a factor of x minus 3 with multiplicity 2, right? Because it occurs twice. So we could say that this has 2 zeros, 3 and 3, or other you can think of it as a repeated 0. So that's where you have to just be careful, because sometimes zeros can be repeated. Okay, so this other function, x cubed plus 4x, if you factor out the x, you get this quadratic x squared plus 4 that has two imaginary solutions. It has 2i and negative 2i. So the 3 zeros that this polynomial function has is 0, 2i, and a negative 2i. Okay, so yeah, so now it's kind of exciting, because previously we would say, oh, I can't factor this any further, but now with our tools, now that we know we introduced I and we introduced complex numbers, we can solve polynomials even further now. So that's pretty exciting. Okay, so let me talk about the zero test, rational zero test. Now, this rational zero test, it basically, so remember rational numbers are like numbers that can be written as a fraction. So all the whole numbers can be written as a fraction if you write them over 1. So that's included in the rationals, the set of the rational numbers. So let's see here. This rational zero test is basically, let me just state it. So if you have a polynomial in this crazy form, this is like the general form of a polynomial where you have a coefficient x to some power n and then the n minus 1 and all the way down to the constant term, right? So every rational zero of f, so rational meaning that it can be expressed as a fraction, so this part doesn't include non-real and it doesn't include irrationals, so like square root of 2 or something. Okay, so every rational zero has this form p over q, and p over q have no common factors other than 1, and p is a factor of the last term, the constant term, so, and then q is a factor of the first term. So basically, how do we use the rational zero test to like help us? How does this help us? Like, why should we care? Well, because think about it. If you have like a very long polynomial and you're trying to figure out what the possible zeros could be, it could be any number, right? Like you don't really, this rational zero test is super important because now it kind of gives us a guide. It helps us narrow down the possibilities for zeros, okay? So, you know, okay, so let's talk a little bit about how to use it. So basically, to use it, we have to first list all the rational numbers whose numerators are factors of the constant term and the denominators are factors of the leading coefficient. So you take the last term, factor it all out, then you take the first term and factor that, and then create all the possible combinations where you have the factors of the n term or the constant term and the in the numerator, and the factors of the first term or the leading coefficient of the first term, rather, in the denominator. So once you do that, you have a list of possible rational zeros. So once you have this list, you can use trial and error to determine if any are actually zeros. So this makes sense. So when you have the leading coefficient as 1, so when you have just like x cubed or x to the 5th or whatever, the rational zeros are just basically factors of the constant term because they're going to be over 1. Okay, so let's try this. So what are the rational zeros of, or the possible rational zeros of this whole thing, x to the 4th minus x cubed plus x squared minus 3x minus 6. So the leading coefficient is 1 here, yeah? Like there's no number here. So, I mean, well, you know, it's like an invisible 1, okay, we should say that. Then according to use this test, we just have to look at the n term, which is -6, and find all the factors of that and consider both signs. So the factors of 6 are 1, 2, 3, and then 6 itself, right? So these are all the possible factors. So then you have plus and minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So now we've gone from like a crazy, infinitely possible zeros, who knows, to now like a shortened list that we can actually try to plug in and see if they work, see if they are zeros, right? So why plug in if we can use synthetic division to find zeros, right? We learned that in 2.4 and we're really pro at it now. So let's go ahead and do that. So we rewrote this f of x as 1, -1, 1, -3, and -6. So these are the coefficients of each term, and this is the constant term. So let's try -1. So if we try -1, you know, bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add, we end up with a 0. So right away, we know that x equals -1 is a 0. So then we take the solution of this, or like the quotient, so 1, -2, 3, and -6, and we go through the whole synthetic division process again, but instead now we just chose 2. So 2 also happens to be a 0. So we bring down 1, multiply, add, multiply, add, multiply, add, and you get 0 at the end. So even further, we've found another 0. So now we have x minus 1 is a 0 and x equals 2 is a 0. So what's left? It's x squared, there's no x term, and then 3. So that's the third factor, would be x squared plus 3. And then we know that if a number is a 0, then x minus this number is a factor. So since x is negative 1, you get x plus 1 is a factor, and since x is equal to 2 is a 0, x minus 2 is also a factor. So now we can restate f of x as a product of these factors. So let's continue. So this x squared plus 3 produces no real zeros, right? Because this is going to be always positive. We can conclude that x minus 1 and x equals 2 are the only real zeros of f. So if you graph it, you can see that it's true. These are the only real zeros. Okay, so what about when the leading coefficient of a polynomial is not 1? Okay, so how can we do that? Well, then what happens is that the list of possible zeros increases a lot. It can become much more complicated. So in this case, we can make it easier by using either a graphing calculator to evaluate the zeros or the potential zeros. We could use a graph to kind of see where the location of the zeros are. And using that graph, then we can calculate and prove that they are zeros. And you can also do the intermediate value theorem with the table to kind of get the approximation of zeros. Lastly, you could do synthetic division, right? Of course. And finding that first zero is usually the most difficult part, but once you found that first zero, it becomes a lot easier, okay? So because when we first we use synthetic division, we find a zero, that shortens our function, right? The quotient has less numbers to work with, so we can keep using synthetic division, okay? So remember, so just a reminder that if we say x equals a is a 0, that's the same thing as saying that a is a solution of this f of x equals 0. Okay, so let's talk a little bit about conjugate pairs, which is nice when you're dealing with finding all the possible zeros, imaginary or real, or however you want to think about it. So let's talk about what are conjugates. Remember that if you have a number a plus bi, the conjugate is a minus bi, and so forth. If you have a number that is like a minus, it's a plus. So they're pairs. So the nice thing about complex zeros is that if you find one, you definitely have the other. They occur in pairs. Okay, so if you have a polynomial function that has real coefficients, and if a plus bi is a 0, then the conjugate is also a 0. But this only works if the polynomial function has real coefficients. So like, for example, this result applies to this x squared plus 1, but not to this function x minus I. That doesn't work. Okay, so let's find a fourth degree. Let's do an example using this idea. So let's find a fourth degree polynomial function with real coefficients that has -1, -1, and 3i as zeros. Okay, so if we say 3i is a 0, and the polynomial has to have real coefficients, we know that the conjugate of 3i, which is a -3i, must also be a 0. So here are your 4 zeros, -1 twice, 3i, and -3i. So now we can write the function in this way by using that linear factorization theorem. We could say, okay, f of x is equal to some constant a, I don't know what, but here's my x plus 1 term, here's my other x plus 1 term, here's my x minus 3i, and here's my x plus 3i. So let's say a was equal to 1. If we multiply the factors multiply these factors together, and we get x squared plus 2x plus 1. And then if we multiply the complex conjugates, remember that it's going to be x squared plus, and then the number squared, 9. And so now we have to take the product of these two, right? So we have x squared plus 2x plus 1 times the quantity x squared plus 9. And then you can use box method or repeated distribution to prove or to show that this is x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. Okay, so let's continue with factoring a polynomial. So just to reiterate, this is the linear factorization theorem where you can write any nth degree polynomial as a product of n factors, meaning whatever the degree of the polynomial, you can write it in, you can rewrite that polynomial as a product of linear factors. What does that mean? Linear factors, that the x has exponent 1 and then it's minus some number, okay? So we have to, if we think of it this way, we need to consider the possibility that some of them are going to be complex or imaginary, right? Okay, so let's say here, if you do not want to get involved with like complex factors, right? We can still write f of x as the product of linear and or quadratic factors. So every polynomial with degree n greater than 0 or positive degree with real coefficients can be written as the product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. They can have imaginary ones, and they do, but no real ones. Okay, so a quadratic factor with no real zeros is said to be prime or irreducible over the reals. So that's just another way of saying prime. Meaning that you can't factor it, you can't have any real zeros. It's prime. So this is different than saying irreducible over the rationals. Okay, so remember that the rationals is a subset of all the real numbers, right? You have all the real numbers that include, pi, square root of 2, square root of 3, all these irrational numbers that cannot be cannot be written as a rational number. Okay, so let's say, for example, here you have x squared plus 1. If I factor this, it becomes the product of x minus I, x plus I. We say that this is irreducible over the reals and therefore over the rationals. Because we don't have, these are not real numbers, right? So it's prime over the reals, okay? So what about this other quadratic, x squared minus 2? This is factorable, but it has real numbers, but they're not rational. Square root of 2 is not rational, okay? So this is considered irreducible over the rational numbers because the answers are not rational, but it is reducible over the reals because these numbers are real numbers. Okay, so let's see. Let's do an example. Find all the zeros of f of x is equal to x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60, given that 1 plus 3i is a 0. Okay, so we know that complex zeros occur in pairs. I said that like 5 minutes ago, right? So since that's true, 1 plus 3i is a 0, 1 minus 3i has to also be a 0. That's just given because they come in pairs. So if one is there, the other one's there, okay? They're BFFs, whatevers. Okay, so what does that mean? That means that x minus, and then in parentheses, 1 plus 3i, and x minus, in parentheses, 1 minus 3i, are factors of f. So let's say, okay, fine. Let's say I want to, let's multiply these two together and see what we get. Okay, so if you do that, you can do this a couple of ways. You can rewrite this problem by using regrouping. You can rewrite this as x minus 1 in parentheses minus 3i and x minus 1 plus 3i. So this is actually just difference of squares, yeah? Because you have something minus something and then that same first term plus the second term, right? So a minus b, a plus b. So if you use difference of squares, you will get x minus 1 squared minus 9i squared, which is basically, it reduces down to x squared minus 2x plus 10. So now, if you want to find the rest, you can divide using long division, right? So x to the fourth, the original function, by this x squared minus 2x plus 10. And using long division, we find that the quotient of these two is x squared minus x minus 6. So you can pause this and go through, x to the 4 divided by x squared, and you can go through all the steps like I showed you last time and verify this answer. So what does that mean? So now what? So now I have now I can rewrite my thing as, okay, x squared minus 2x plus 10, which happens to be irreducible over the reals, right? And then I can write x squared minus x minus 6. That is factorable. It's not prime, as the product of x minus 3 and x plus 2. So now you have, here it is, f of x written as 3 terms. This one could be split up, right? And we saw that earlier, it was. But here are the zeros. So what are the zeros? Finally, you have 1 plus 3i, 1 minus 3i, then you have 3 and negative 2. So also, if we didn't know that 1 plus 3i was a 0, we could have still found all the zeros of the function by using synthetic division to find the real zeros, negative 2 and 3. So then we could have factored the polynomial, we could have rewritten the polynomial as the product of these factors, x plus 2, x minus 3, and then this would have been the quotient x squared minus 2x plus 10. But then when we got to this point, we could have used quadratic formula. So make sure you are very well versed in quadratic formula, and make sure that it's easy for you. So you would use this to get x equals 1 plus 3i, 1 minus 3i. Okay, so then the last thing I want to talk about is other tests for zeros of polynomials. Okay, and I'm not going to go too deep because I think the first thing to do is really just understand how to break it down as much as you can, and then these are just like little tips, little tricks. Okay, so we know that an nth degree polynomial can have at most n real zeros, but a lot of them do not have that many real zeros. So let's say, for instance, x squared plus 1 has no real zeros, and f of x equals x cubed plus 1 has only one real zero, right? So how do we know? How can we tell? If there was only a way to figure out how many real zeros a polynomial has? Oh my goodness, there's a theorem. Yes, it's called Descartes' rule of signs. So if let's say you have a function and it's a polynomial, right, from in this general form, some polynomial with real coefficients, and then the last term is non-zero. Then the number of positive real zeros is equal to however many times the sign changes. Okay, so let's say I count, this is positive, this is negative, right? That's one sign change, and then this was negative to positive, that's two sign change, and so on. So if I count the number of sign changes, it's either that's how many positive real zeros there are, or there's n minus 2 many. So like if I found 3 sign changes, for instance, it's either they have 3 positive reals, or they have 1 positive real zero. Okay, now to find the negative real zeros of f, you can either just you can plug in a negative x, okay, simplify that, and then count the sign variations, the sign changes. Okay, so it's either the same amount of sign changes or 2 less. Okay, so remember that here what it says, variation in sign, just means that the sign changes. They say it's so crazy, right? Okay. Well, let's just look at it. Okay, so when using this rule of signs, a zero of multiplicity k should be counted as that many zeros. So let's say, for instance, here we have the polynomial x cubed minus 3x plus 2, right? So it changes sign. So it's positive to minus, so that's once, and then it becomes negative to positive, so that's twice. So it has 2 variations. So either it has 2 positive or no positive real zeros. So when we factor this, we say here, you have x cubed minus 3x plus 2. You have a multiplicity of x minus 1 has multiplicity 2. And then we have here x plus 2, right? So we have 2 positive real zeros. Are x equals 1 because it occurs twice, so multiplicity 2. So using the test, there was 2 positive real zeros, which is just, it was a repeated 0. Okay, so now let's do another one. So let's say you have a cubic function, 3x cubed minus 5x squared plus 6x minus 4. And if you're following closely, you could count the number of sign changes with me, okay? So this is positive to negative, right? So that's 1 sign change. Here's another one. Oh, so it's probably, so positive to negative, negative 5x squared to positive 6x, that's the second sign change. And then positive 6x to negative 4, that's the third sign change. So what does that tell us? It either has 3 positive real zeros or 1, right? 2 less, right? So it either has 3 or 1. So it has here now, so it's either 3 positive or 1 positive. Okay, now let's look at the negative real zeros. So let's plug in negative x and simplify. So here we go. It's negative. Let's plug it in, and remember when you square a negative, you get a positive, right? Now notice they're all negative. So every single term is negative. So does it change sign? No, it does not, right? So, so what can we say? We can say that basically there's no negative real zeros. So check it out. So if we were to graph it, and we did, so there it is, it only crosses the x-axis once. So it only has 1 positive real zero. So the test holds true. Okay, and then we have this other test that has to do with like the upper and lower bound. So basically, you can take a number. What is an upper bound for the real zero? So a number is an upper bound if there's no zeros that are greater than that number. And a lower bound would be where there's no real zeros less than that number. Okay, so how do we figure out what upper bound and lower bound? Like, how do we know? So let's say you're using synthetic division to divide f of x by some linear factor, okay? X minus c, who knows? If c is positive, and every number in the last row is either all positive or 0, then you would say that c is an upper bound. So, that means you shouldn't go any higher to look for zeros. And you might even be able to see how this could be helpful, because if you use this test combined with the rational root test, you could knock down some numbers, right? Okay, so if you plug in a negative number using synthetic division, and then the numbers in the last row are alternatively, like they alternate positive and negative signs. Zero counts as either positive or negative. Then you would consider this a lower bound. Okay, so you can kind of, if you know an upper bound and you know a lower bound, then you know that the actual zero will be between there. Okay, so let's see here. So then finally, don't forget to factor, basically is what I'm trying to say here. So if you have a common factor, make sure you take it out before you start applying all the tests that we've covered today, because that will make it a lot easier for you. So you can just reduce it here. Like let's say here we factored out an x. By factoring it out, we know that x equals 0 is a 0. X equals 0 is a 0. And then whatever's left, we can, do all our signs, all our tricks that we've learned. Okay, so that's it for me. This is your homework, and please be on the lookout. I will post some worked out examples on our the page for chapter 2. Okay, thanks for listening, and I'll see you on the next video.